Good evening, Doctor. My name is Wei Yan, and today our group team will be presenting assignment 2, which focuses on the comparative study of BJT and FET amplifier for a low code sensor signal amplification module. This is our group member list. So this study focuses on the development of a low code signal amplification module for sensor applications. So in many sensor systems, the output signal is usually weak and needs amplification before further processing. So since cost and performance are both important and essential, so this project compared BJT and FET technology to determine the most suitable amplifier for sensor interfacing, IoT devices, and low power embedded system. So in this study, the performance of BJT and FET amplifier is analyzed and compared. So the comparison focuses on key factors such as amplification performance, power consumption, input and output impedance, noise performance, and cost and the effectiveness in sensor application. To begin the technical discussion of the study, so firstly, let's look at the bipolar junction transistor or BJT, which is one of the transistor technology considered in this comparison. So a BJT is a semiconductor device that is widely used for amplification and switching application. So it uses both electrons and hole for conduction, so which is why it's called bipolar. And there are two main types of BJT, namely NPN and PNP. So at the moment, let's have a look on the structure of the BJT. So a BJT consists of three semiconductor regions that form two PN junctions, and it has three terminals. So the first one is emitter, second base, and the third one is collector. So the emitter supplies charge carrier, the base controls the current flow, and the collector collects the charge carrier. So there are two types of BJT, which are NPN and PNP. The main difference between them is the arrangement of the semiconductor layers and the directions of the current flow. So in an NPN transistor, the current flow when the base is positive, while in PNP, the current flow when the base is more negative than the emitter. So in addition, the base is very thin and slightly doped, allowing a small base current to control a much larger collector current. So now let's take a look at the operation of a BJT and its characteristic curve. So from this graph, we can observe the three operating regions of a BJT. So the first one is cutoff region, the second one is active region, and the third one is saturation region. So for the first one, the cutoff region is under the nearly at the below of the graph, so where the transistor is off and almost no collector current flows. So the second one is the active region, so where the transistor works as an amplifier and the collector current is controlled by the base current IB. So the third is the saturation region, so where the transistor is fully on and it is acting like a switch. So overall, this graph shows how a BJT can operate either as an amplifier or a switch. So now let's move on to another important parameter of a BJT, which is its current gain. So represented by beta. So current gain shows how effectively the base current control the collector current in a transistor. So it is defined as beta equal to IC over IB. So this means that even a small base current can produce a much larger collector current. Therefore, a higher beta value means the transistor has a greater ability to amplify signals. Overall, the bipolar junction transistor is an important semiconductor device that plays a major role in electronic circuit. So it can operate either as amplifier or switch depending on its biasings and operating region. So by using a small base current to control a larger collector current, so the BJT is able to perform efficient current control and signal amplification. So due to all of these characteristics, the BJT is widely used in many electronic devices and circuit applications. Thank you.
All right, now we are looking for the JFET structure. So, what is JFET? JFET is actually an acronym of Junction Field Effect Transistor. A JFET consists of a semiconductor channel through which current flows between the two terminals called source and drain. On both sides of the channel are gate regions that form a PN junction with the channel. The gate controls the flow of current by varying the width of the channel. There are two types of JFETs, which is N channel and P channel. In the N channel JFET, electrons are the main charge carriers, while in the P channel JFET, holes are the main charge carriers. The JFET structure allows it to operate with high input impedance and low power consumption, making it useful in amplifier and switching applications. Okay, now we are talking about metal oxide semiconductor field effect transistor, which also called MOSFET. So a MOSFET consists of three main terminals, which is the source, drain, and gate. The source and drain are formed by heavily doped semiconductor regions, while the gate is placed above the substrate and separated by a thin insulating layer of silicon dioxide. The insulating layer prevents direct current flow between the gate and the channel, giving the MOSFET a very high input impedance. The gate voltage creates an electric field that controls the current flow between the source and the drain. MOSFETs are available in N channel and P channel types, and they are widely used in electronic circuits for switching and amplification due to their efficiency and low power consumption. Well, here's the operating regions of a MOSFET, which are shown in its characteristic curves. The first region is the ohmic region, also known as the linear region. Here, the gate voltage is high enough to create a channel, allowing current to flow between the drain and source. The MOSFET behaves like a variable resistor in this region. The second region is a saturation region. In this region, the MOSFET is fully turned on, and the drain current becomes nearly constant, mainly controlled by the gate voltage rather than the drain voltage. And the third region is the cutoff region. In this region, the gate to source voltage is below the threshold voltage. So, no channel is formed and the MOSFET remains off. As a result, almost no drain current flows.
Assalamualaikum warahmatullahi wabarakatuh. My name is Zikri Ilhamananda Putra, and I will explain the comparison between BJT and FET. So let's start with BJT first. Here we have the circuit schematics and then the input and output voltage graph. The input voltage is represented by the red lines, and the output voltage is the green colored lines. The input resistance, I use the approximate analysis to calculate the input resistance. And the first thing we need to do is to make sure that we can use the approximate analysis using the calculations above. And then once it is satisfied, then we can directly calculate the input resistance. For the output resistance is basically the resistor in the collector. Next one, we have the MOSFET. Uh, the circuit schematic is displayed at the top right corner, and below it is the output voltage versus input voltage graph. The output voltage is the one with yellow colored line, and then the input voltage is the purple colored lines. The input impedance is just the parallel of R1 and R4, which is 2.2 kilo ohm and 1 kilo ohm. And the output impedance is just the resistor across the collector.
So for our next comparison, it's going to be the power consumption of the BGT and the FET. Uh, as we know, the BGT is current controlled, so it always needs a base current flowing for it to operate. So that means it's going to be drawing power even when it's in standby, compared to the FET, which only has a tiny bit of power current leakage, but other than that, it can stay idle without burning power. That's why we use it for portable batteries and battery powered devices. Now, moving on to noise performance, BJT has inherently produces more noise because it is a bipolar device where current flows through the majority and minority carriers. So it exhibits thermal noise and shot noise. So it makes it generally more noisier, while FET is a unipolar device, and then current only flows through the majority carriers, so we only get thermal noise. Although that is the case, BJT does have less flicker in higher frequencies than the FETs, and that's why we use BJT for RF and then FET for precision low frequencies. Thermal stability is where BJT takes the biggest hit because they're very prone to higher temperatures. As the temperature increases, their beta value increases, which increase the collector current, which generates more heat, which in turn increases the risk of thermal runaway compared to FETs, where more temperature it can still work because they have basically a drain current that naturally decreases as the temperature increases, so it resists thermal runaway. Moving on to switching speeds, BJTs they store more minority carriers in their base, so it can cause a turn-off delay. This is because the carriers they need to recombine before the device turns off, and so it is very slow during switching. While FETs there are majority carrier devices, so the turn-off is not limited by the the carriers recombining. The one advantage BJTs have over FETs is their manufacturing process. They have lower per unit cost for their discrete components, so they're easier to produce and they're ideal for person to person and personal use, maybe like for hobbies and maybe cost sensitive designs. But when it comes to FETs, they're more complex to manufacture, so they are more expensive to get singular ones, but then when you go large scale ICs, the cost per transistor becomes pays off compared to BJTs.
Hi, I'm Mohammad Shafizal bin Sabri. So now looking at both sides together in this table, we can clearly see the differences between BJT and FET across all 8 parameters. The values here are taken directly from our own simulation results in sections 3 and 4. So based on our results and analysis, here is our engineering justification. FET performed better in most parameters. It achieved a higher gain of negative 35.9 compared to BJT's negative 30. Its input impedance is near infinite, meaning it doesn't load the source at all. Unlike BJT, which only had 688 ohms. FET also consumes less power since the gate draws almost zero current. It's thermally stable on its own without needing extra components. And it switches faster because it only uses majority carriers.
Hello, I'm Mohammed Bilal, and I'll be talking about our final recommendation for our project. So far we have gone through the BJT and FET and all the details. So I'll just wrap it up. So we have the two options BJT and FET, the common emitter and common source. You can see in the BJT there's a high theoretical gain on paper with the AV value of negative 30. But there is a critical loading bottleneck because of the low input resistance. It can pose a high risk to raw signal integrity. There's transducer distortion. As for the FET, it has advantages because it's superior in signal preservation due to insulated gate structure, which yields a near infinite structural input impedance. It has no loading degradation and optimal module efficiency because it's strictly voltage controlled, which naturally will eliminate any steady state static power losses. So our final decision, our recommendation is to use the common source, the FET, because it is mathematically and operationally superior for this specific application. So continuing from what we mentioned previously as our final recommendation, the FET common source. So I'll give a short justification and alignment. So we believe, based on our research, that our choice is, if we consider performance and budget, the most optimal choice. It also has the best thermal runaway prevention and highest thermal stability. As for the industrial application alignment, in accordance with our target, uh, since it has sensor interfacing, high input impedance, which natively prevents signal degradation when connecting to a standard industrial analog transducer. It also has remote IoT telemetry and system durability, which can operate under variable field conditions. And yeah, that's it from us, the six crew. Thank you very much.